Okay, on the first one, we want to rank the three atoms based on their electronegativity. And I have, this is kind of an easy one. So iodine would be the strongest, most electronegative because it's the closest to fluorine, followed by strontium, followed by rubidium. And I am just looking at the periodic table to rank those. So these are all in the same row. Iodine is the most to the right, followed by strontium, followed by rubidium. And we can kind of do the similar type of thing with calcium and magnesium because they're in the same group, and so is strontium. So these are in the same column. And since they're in the same column, the one at the highest would be the one that's the most electronegative. Now, bromine and calcium, potassium, all in the same as well. So bromine greater than calcium, greater than potassium. All right, question 2, it wants us to use the electronegativity values to tell if these are covalent, polar, covalent, or ionic. Now, the first one I kind of know is ionic, and it's because it is a metal and nonmetal. But using that table 12.3 they're talking about, we would see potassium has an electronegativity value of 0.8, and chlorine is 3. The difference between those two is 2.2. So up here in that very dark area, which is the ionic. Now, next one is bromine and chlorine. Now, they are both nonmetals, so this has got the covalent part, but is it covalent / nonpolar covalent or polar covalent? We can tell that by the difference in the values. And while bromine and chlorine are right on top of each other, the electronegativity differences are close. And only a 0.2 difference, we can say slightly polar covalent. But actually, that's very close to being nonpolar because of how close they are. That is down here in the very low difference. So we're not at 0, which would be the covalent. We're in that intermediate range, so we can say it's a polar covalent. So slight unshared electron. But since these two are the exact same thing, that is just going to be covalent, evenly shared. All right. Next thing we want to do is looking at these diatomic, we want to know which end of the molecule is more positive related to the other. Well, this is kind of applying that electronegativity difference. The one that's more electronegative is going to have the electrons. The other one will be positive. And since we have something like this, where we have a situation where fluorine is the most electronegative and everything goes towards fluorine, we can use that as a basis of identifying. We know fluorine would be the more negative, so in this first one, hydrogen is the positive. Next one's the same thing. We've got chlorine versus fluorine. Chlorine would have to be the one that's more positive. Now, when you don't have fluorine on there, like this next one, iodine chloride, the one that's going to be the positive one is the one that's furthest away from fluorine. Iodine will be the positive one. All right, we're going to do that same thing with this next groupings, but we're going to use the little dipole arrow or the symbols to distinguish these two. What I mean by the dipole arrow, since fluorine is the more electronegative atom always, we're going to show the electrons being pulled towards it and put a little positive there to symbolize that that's the little dipole arrow. And that applies anytime we have something that's more electronegative. Now, on all these, we're comparing it to phosphorus, and we could look at the number and see phosphorus is a 2.1, and actually that's smaller than both carbon and oxygen, our other two. So all of these have that same arrow going from phosphorus to the other atom. And we could have also done these without the arrow, but with the little Debye symbol. So the Debye symbol is the little delta looking thing. And you have a positive end and a negative end. Okay. Number 5. On the basis of their electron configurations, predict the formula of the binary ionic compound likely to form when the following pairs of elements react. Boy, that seems like a lot of words. What they're basically asking is, what ionic formula would you make? So since sodium, for instance, likes to form a positive ion and sulfur likes to form a -2, you would expect that to be Na2S. Next one would just be MgBr2. The next one would be lithium, 3 lithiums and nitrogen. All right, size is interesting. Now, when we introduced the periodic table as a trend, we actually, I'm going to draw the periodic table here real quick. We introduced this idea that the size got bigger as we go down. And that's very true when we have neutral starch species. But these are ions. Now, the ions can be kind of interesting. Like B might be an easy one to see because we have calcium versus a calcium 2+. Well, if you remember, those extra electrons took up space, making a 2+, we go and take it back to a noble gas, which are on those small side. So this wants to know which species is larger. The Ca2+ is the larger one, and that's mainly because Ca is, reverse that. Ca is the larger one, and that's because Ca2+ is closer to the size, let's say that is closer to the size of the noble gas would be as a 2+, so it's going to be closer to the size of argon. And technically be a tiny bit smaller than argon because it technically would have the exact same electrons as argon, but a much bigger positive nucleus pulling in on it. And yet the calcium with those extra 2 electrons, really big. All right, now on the sodium and chlorine, sodium ion would actually make that closer to neon in size, where the chlorine one is closer to argon. So we're going with chlorine negative because it is actually a larger noble gas. Closely related to a larger noble gas. Now, this C is kind of interesting. Cesium +1 would have the same electrons as xenon. Iodine Midas would have the same electrons as xenon. So the electron cloud for both of these is identical to xenon. The larger species is that I- then. And the reason is, while they're both the same size as xenon, iodine has a smaller nucleus. And the important part about that small nucleus has fewer protons, so less of a positive charge pulling it in. All right. Page 2 on this involves our Lewis structures. We're going to actually do a couple questions before we start those. And really the interesting one is this first thing. It's just, what does it mean when 2 atoms in a molecule are connected by a triple bond? Well, the easiest triple bond I can think of is just what happens between 2 nitrogens. And all a triple bond is when two atoms share 6 electrons. All right. Part 8 is where we're doing our Lewis structures, and we're just going to do those for all these here. Now, I don't ask for it anywhere on this, but I actually, in this corner up here, I put down the valence electrons for the entire atom or the entire molecule. So I have 4 electrons from carbon, and I have 7 for each fluorine. So that'd be 42, 46, 50 valence electrons. And I'm going to place them by connecting the carbons and then connecting 3 fluorines to each one of those carbons. Excuse me. That took care of 2, 4, 6, 8, 10, 12, 14 electrons. And I'll just go around here and put electrons around each of those fluorines to make them happy. And that's all my electrons. All right, so I have a nice Lewis structure here. Now, the shape on this one is technically got 2 answers because I have 2 atoms that could be considered as the central. Now, they're both carbon, and each one of those carbons has 4 things on it. So it's tetrahedral at both carbons. And being tetrahedral, we go with the 109.5 bond angle. All right, and I noticed something on that. I need this to be larger. Oh, that's not an insert page. What the heck? Did I just, I just copied that page. What I need to do is zoom in on this. Is that all I can zoom in? Okay. Yeah, all right. That's going to help me write on this small print. Okay, next one here. Silicon, just underneath carbon, also has 4 valence electrons, and those fluorines still have 7. So this is 32 valence electrons. This is going to look very similar to that previous one. Actually, silicon, I have a fluorine, I have a fluorine, I have a fluorine, and I have a fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And that would be tetrahedral as well, because we have 4 things coming off the central atom. And so still 109.5 bond angles. Okay, C2H4, 4 valence electrons, 1 valence electrons, 12. Yep. All right. I'm going to bond the 2 carbons to each other and put 2 hydrogens on each one of those carbons. Get everything evenly distributed. All right, that's 2, 4, 6, 8, 10. Now, if I put those electrons just on one of those carbons, it would make that carbon happy, following the octet rule, but not the other one. So I'm going to instead put those 2 electrons between the 2 carbons and have both carbons share it. That's 2, 4, 6, 8, 10, 12 electrons. That is our structure. Now, each one of these carbons has just 3 things. So, trigonal planar at each carbon. And so bond angle will be more like 120 degrees. All right. I don't know why I have NO2 here. 5 valence electrons and 6. Excuse me. All right. I wonder if I wanted to have that as nitrite. I'm going to put it down here. I'm going to do NO2, but I'm also going to do NO2 negative. All right, so this thing has altogether, let's see, 6 times 2, 12 plus 5, 17 valence electrons. The odd number of valence electrons makes that kind of an interesting problem. Now, the reason I say interesting problem is we are going to see that any atom with an odd number of electrons is what we can consider a radical or a free radical, and that makes this actually kind of reactive. Because no matter how I do it, I'm going to end up breaking the octet rule with an odd number of electrons. All right, but I'm going to start this by putting the nitrogen in the middle and having an oxygen on either side. 2, 4, 6, 8, 10, 12, 14, 16, and I'll put the last one there. All right, but if you notice something, that middle atom is not happy. It's not fitting the octet rule because it's only seeing 2, 4, 5 electrons. So I'm going to kind of fix that by taking 2 of these electrons and making that as a double bond. But now we have an odd dilemma that we can't answer yet. So what I mean by the odd dilemma, that central atom is not following the octet rule. But maybe, I'm going to do this in different color, maybe what I should have is I'm going to take that electron in one of these and make another double bond and then have the oxygen have the odd number of electrons. It kind of goes back to which would be better, having the odd electron on the oxygen or on the nitrogen. But either one, we're going to have a break in the octet rule. And the shape's going to kind of be different on these two because this one actually is going to count like 3 things. 1, 2, and then a lone electron. This was actually going to be more like 2 things. So the red one would be bent on its shape and bond angle around 120. The other one is going to be linear. I'll do this in blue. And more like 180. And at least at this point, it's not obvious which one's correct. Now, I suspect what I actually wanted, and I just don't have it on this correct. I bet I wanted nitrite, which I'm going to do down here. And nitrite is NO2 minus. And the reason that helps us is because we're adding one more electron to it. And what's neat is with this, I can take this structure I ended up with in red and add one more electron to it. Make one of those a double bond, make that now a pair rather than a single bond, and only this far one like that. But when it's an ion like that, the polyatomic ion, it actually balances out the charge, and it's not a free radical. It makes it really darn stable. Bond angle would be about 120 degrees because I have two oxygens and a lone pair. But it does appear, and this is the raw file, so this is what I've sent to you. So I did have NO2 there, which does end up with a free radical. Okay, H2SO4, one valence electron, 6 and 6. So let's see, that's 32 valence electrons. So it's a polyatomic ion, the SO4 is. So I'm going to do that with the SO4 in the middle. And I'll do O, 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 O. And the two hydrogens I'm going to attach to two different oxygens. And I'm just doing them out on the ends to make it easier to draw. Well, that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yeah, that'll work. All right, now shape. Are our oxygens like that? We could be asking for that shape. We'd have bent with 109.5 degree bond angles. And around our sulfur, we have tetrahedral, also 109.5 degree bond angles. All right, next one here, hydrogen phosphate ion, HPO4 2-. 1, 5, and 6. So 6, 24, 29, 30, 2-, 32. I'm going to kind of do this like I did with the sulfate and have the phosphorus making the phosphate first, and then add that single hydrogen just to one side. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And our shapes are almost the same as up above there. Bent, tetrahedral. Now what's kind of interesting, these guys aren't really adding too much to it, because when you total up your electrons here, you'll see this is still 32, and same here, 32. And all we're going to see that's different on this second one is we're going to have another hydrogen off there. On this one, we're just going to have one fewer oxygen from that top one. So instead of having that line, I'm going to have a lone pair. Basically, on these guys, that hydrogen goes on, doesn't actually bring any electrons. You kind of start with this phosphate ion, and when you add a hydrogen, you take those electrons and make the bond. When you add another hydrogen, you take those electrons and make a bond. And technically H3PO4, the base one, I would just add another H. I can do that here, blue. Just take those electrons and add another hydrogen. But shapes are the same. Around the oxygen, bent. Around the phosphorus, tetrahedral. This one only has the phosphorus, so it is tetrahedral. And we have all 109.5s. Not too bad, huh?